The Doppler Effect is going to be the topic of this lesson in my new general physics playlist, which when complete will cover a full year of university algebra-based physics. Now we're going to apply the Doppler effect to sound in this lesson, but we'll see at the end of the second semester topics that can also be applied to light, and I'll kind of refer to that very briefly. Now the Doppler effect allows us to explain why the observed frequency might be different than the actual frequency of sound that's being emitted by a source. So depending on if the source and the observer are moving relatively towards each other or moving relatively away from each other. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, if you're new to the channel, we've got comprehensive playlists for general chemistry, organic chemistry, general physics, and high school chemistry. And on chadsprep.com, you'll find premium master courses for the same that include study guides and a ton of practice. You'll also find comprehensive prep courses for the DAT, the MCAT, and the OAT. Now, the Doppler effect is something we've all experienced and maybe have a little bit of familiarity with, and I like to think of it in the context of like a Formula One car race. And so if you're sitting right next to the track and these cars come around the curve and go right by you, there's a peculiar sound that you hear, and it's something to the effect of so, and as the cars are coming towards you, you experience a higher pitch. So as humans, we hear higher frequencies as higher pitch, but as they go past you and start moving away from you, all of a sudden those same cars you observe a lower pitch or lower frequency. So, and that is because of the Doppler effect. So if we take, for example, a slightly different example that's unrelated to sound for just a second. So, but let's say I've got a bag full of baseballs, and I'm going to start throwing baseballs at you at a rate of 1 per second. So, and I'm just going to stay here, and you're going to stand there and take it, and I've got really good aim, and I never miss. And so as long as I keep throwing baseballs at you at 1 per second, you're going to get hit with a baseball at a rate of 1 per second. Now that's example number one. Now in example number two, instead of just both of us standing here, I'm gonna run towards you at the same time. And so I'm still gonna throw baseballs at you at a rate of 1 per second, but now I'm gonna get closer and closer and closer to you the whole time. And as a result, you're no longer going to get hit with a baseball at a rate of 1 per second. You're going to get hit with a slightly faster rate because each successive baseball that I throw has to travel less distance before reaching you because I'm moving closer and closer and closer to you. So as a result, the rate you experience getting hit by baseballs will be slightly higher than 1 per second. Now, the same thing would experience if you get tired of being hit by baseballs. Instead of me running towards you, you run towards me. And the same thing, each successive baseball I throw is going to have to travel less distance before hitting you. And once again, you're going to experience at a rate that's slightly faster than 1 per second. And so whether the source is moving towards the observer or the observer is moving towards the source, either way, the observed frequency is slightly faster than the actual frequency from the source. Now it works the other way as well. So instead of running towards you this time, so I'm afraid of you and I'm throwing these baseballs at you to kind of keep you away from me, but I'm running backwards at the same time to get away from you. And so as a result, I'm still throwing them at a rate of 1 per second, but now because each successive baseball has farther to travel before reaching its target, you, so they're going to hit you at a slightly lower rate than 1 per second. Now the same thing can be accomplished as well with, instead of me running backwards, what if you run away from me? So and as I throw them again at you, again, each successive baseball has further to travel than the previous one and will take longer to reach there. And so again, the rate at which the baseballs hit you is going to be slightly lower than 1 per second. So, and again, whether it's the source or the observer, as long as they're moving away from each other, relatively speaking, so the observed frequency is going to be lower than the actual frequency. And it works effectively similarly with sound. So the frequency that's observed, as the wavelengths are traveling from the source, how fast they reach the observer depends on if, the source and the observer are stationary, whether they're moving towards each other. If they are, then the number of wavelengths that reach the observer is going to be higher, at a higher rate anyways. So than the actual emission of wavelengths coming from the source. And if the source and the observer are moving relatively away from each other, then it's going to be the opposite. Then the observed frequency, the number of wavelengths per time, that kind of reaching the observer, is going to be lower than the actual emitted frequency from the source. So now let's take a look at the actual equation for the Doppler effect. It looks a little bit daunting, but it's not as bad as you think. Now, FO here stands for the observed frequency. FS stands for the frequency of the source, the actual emitted frequency from the source. So, and then V0 is the velocity of the observer. So V source is the velocity of the source. And then V here is the velocity of your wave. In this case, it's going to be the velocity of sound. But if we were dealing with light waves instead, then it would be the velocity of light, or speed of light instead. All right, so the way this works, so we can memorize when you need to either add or subtract the velocity of the observer to the speed of sound, or when you need to subtract or add the velocity of the source to the speed of sound of the denominator. And I can give you rules for that. And I could say, well, if the observer is moving towards the source, you add it. And if the observer is moving away from the source, you subtract it. So, but if the source is moving towards the observer, then you subtract it. And if the source is moving away from the observer, then you add it down here in the denominator. And you can just memorize those rules. But then you got to memorize 4 different rules and memorize those situations where if you understand in principle what should happen, then you can make it mathematically happen. And much kind of better way for getting this down pat without having to memorize too much. So keep this in mind. As long as the source and observer are moving relatively towards each other, whichever one, overall, the observed frequency should be bigger than the actual frequency emitted by the source. So that's going to be the key to kind of figuring this out. So let's talk about the velocity of the observer first. And let's say that the observer is moving toward the source. Well, if the observer is moving toward the source, then the observed frequency should be higher than the actual frequency of the source. And for that to happen, what do I need to do with this number right here? Well, in this case, I would need to add that number to make the numerator larger. And so if the observer is moving toward the source, add in the velocity of the observer because it's going to make this ratio larger than 1, which is going to make the observed frequency bigger than the frequency of the source. Okay, works exactly the same way in the opposite direction though. What if the observer is moving away from the source? Well, in that case, then the observed frequency should be lower than the frequency of the source. And to make this ratio come out less than 1, well, then I would need to subtract the velocity of the observer instead. So to guarantee that happening. And that's exactly how it works. And so instead of memorizing it, you can just kind of mathematically look at it and say, well, if the velocity, if the observer is moving toward the source, I need this ratio to come out bigger than 1 so that the observed frequency is bigger than the actual frequency. And so I need to add the velocity of the observer. Great. And subtract the other way around. Okay. Now in the denominator, it works a little bit differently, right? So for the denominator, so if the denominator gets bigger, that means this ratio is going to be less than 1, and the frequency observed is going to be less than the frequency of the source. If the denominator gets smaller, then this ratio is going to go larger than 1, so the other way around, and then the frequency observed is going to be bigger than the frequency emitted by the source. So that's why things are going to be a little bit backwards, and that's why it's going to be minus over plus. So now if the source is moving towards the observer, well, if the source is moving towards the observer, again, the observed frequency should go up. The observed frequency should be higher than the actual emitted frequency by the source. So this ratio needs to be larger than 1. And if I subtract the velocity here, so that's going to make the denominator smaller, which is going to make the overall ratio larger and make it so that the observed frequency is indeed larger than the frequency of the source. It'll work the other way around though. Now if the source is moving away from the observer, so in this case now I'm going to add the velocity of the source. That's going to make the denominator larger, and if I make the denominator larger, it's going to make the overall ratio smaller than 1, and the observed frequency will now be less than the frequency of the source. So that's how it works. Now if you want to memorize all 4 instances, more power to you, but if you can just understand mathematically what needs to happen, if the observer and the source are moving towards each other, make sure whatever you do, that frequency observed comes out larger than the frequency of the source. And if the source and the observer are moving away from each other, then whatever you do, make sure that the observed frequency comes out smaller than the actual emitted frequency by the source. So now we're ready to work a couple of examples. And first one here says a stationary ambulance, that means not moving, is emitting a sound with a frequency of 500 hertz. Well, let's draw this out just a little bit. So we've got an ambulance, and I'm not a very good artist here. So, and this one is stationary, so its velocity is 0, and we'll call that the velocity of the source of the sound. And if you are moving toward the ambulance with a velocity of 34 meters per second, what is the frequency of sound you observe? And use the speed of sound of 340 meters per second. So then there's you over here, and you're moving towards the ambulance with a velocity of 34 meters per second. You're the observer, so we'll call this VO. So, and my first question for you in this case might be, is the observed frequency going to be higher or lower than the actual frequency of 500 hertz? Well, again, as long as the source and the observer are moving towards each other, relatively speaking, which is the case here, so then the frequency should be higher that is observed as compared to the actual emitted frequency of the source. And so in this case, we should expect an answer that's going to be higher than 500 hertz. So let's plug some numbers in here. So the frequency observed equals the frequency of the source, which in this case is 500 hertz. So, and then times ratio of speed of sound, which we're told to use 340 meters per second. And then it's plus or minus the velocity of the observer, which is 34 meters per second, and then all over the velocity of sound, 340 meters per second. And since the source is stationary, it'd be minus or plus 0, which is still just 340. And from here, you could just plug this all into your calculator and let it do the heavy lifting for you, but you still need to know, are you adding the 34 or subtracting the 34? And you got two ways to approach this. You could have memorized, well, when the observer is moving towards the source, you add the velocity of the observer. Okay, great. If you memorize that rule, one of the 4 rules you need to memorize, you're good to go. The other thing you could say is this. Again, since the observer and source are moving towards each other, relatively speaking, that means the observed frequency has to go up. It needs to be higher, which means this ratio needs to go up. And what's going to make this ratio go up? Adding 34 or subtracting 34 in the numerator? Well, if I want that ratio to go up, I want the numerator to get larger, and I need to add it. That's where we're going to add that 34. And so in this case, we're going to get the observed frequency. It's 500 hertz times 374 meters per second, all over 340 meters per second as a ratio. And it turns out that that ratio happens to equal 1.1, which times 500 hertz, plug it into your calculator, is going to get us 550 hertz. And there is your correct answer. Now, cool, I'm assuming, again, you let your calculator do the heavy lifting. Notice I didn't actually pull my calculator out because I wrote the problem, but I used nice numbers here. And you could actually get away on this one of not using the calculator. And I don't really care if you use your calculator or not, but there's an interesting point, big take home, big overarching principle you want to see here. So if we take a look at this, what I want to do is actually, instead of adding these together and then dividing by 340, I want to actually divide each of these separate terms, since they're added, by 340 separately first. And so in this case, this would turn into frequency observed is 500.0 hertz. 340 over 340 is 1. 34 over 340, notice that 34 is exactly 10% of 340. And so 34 over 340 is 0.1. And so all of a sudden, so what's going to happen to our 500 hertz? Well, we're going to have its value plus an additional 10%. So, and this is the way it works. So if the observer is moving with a velocity that is 10% the speed of sound in this case, if we were dealing with light, then it would have to be 10% the speed of light, but 10% of the speed of sound in this case, that means the observed frequency is either going to go up or down by 10%. If the observer is moving toward the source, it goes up by 10%. If the observer is moving away from the source, it would actually be subtracted here and go down by 10%. But the key is, it all depends on how fast is the observer moving relative to the speed of sound. Whatever percent of the speed of sound it is, that's how much the frequency is going to change. Cool. So, and that's a great thing for ballparking answers and seeing if answers make sense and things of this sort. So let's see the next one, though, and see how this works out. So the second problem is very similar to the first one here, but we're going to switch things around a little bit. An ambulance is emitting a sound with a frequency of 500.0 hertz. So far, same thing. If you are stationary this time, so let's change this up. So now it's you, the observer, that's going to be stationary, not moving. So velocity is 0. All right, if you are stationary and the ambulance is moving toward you with a velocity of 34 meters per second, what is the frequency of sound you observe? And again, use the velocity of sound of 340 meters per second. Okay, so now it's actually the source that's moving, not the observer. Well, the source we account for in the denominator, not in the numerator. And so it turns out this is still going to be like, well, the source is moving with 10% the speed of sound, Chad. Shouldn't that change things by 10%? Almost. Not quite exactly 10%, it turns out. It's close. If you ballparked it around that number, you'd be within spitting distance, but you wouldn't be exact. And the idea is this: if you change the numerator by a certain percentage, you've changed the entire number by a certain percentage. But when you change the denominator by a certain percentage, that's what you're dividing by. And it actually doesn't change the entire number. So by the same percentage, it's just close. So if we take a look at how this is going to change things up here. So all of a sudden now, let's just rewrite from here on down. So now it's going to be plus or minus 0. The observer is no longer moving. But on the denominator, it's going to be 340 meters per second minus or plus that 34 meters per second. And again, we should realize, is the frequency that's observed going to be higher or lower than the actual emitted frequency of the source? And again, because the observer and the source are moving towards each other, relatively speaking, and I guess that arrow should change as well. It's actually this way around. So, but because they're still moving towards each other, the observed frequency should be higher than the actual emitted frequency of the source. So how do I make that happen with a minus or plus in the denominator? Well, in this case, if this is the observed frequency is gonna be higher than 550, again, I need to make this ratio go up. How do I make this ratio go up? By subtracting or adding this 34. Well, in this case, if I add it, that would make the denominator bigger, which would make the overall ratio smaller because I'm dividing by a larger number. And so in this case, we actually want to subtract it instead. And if I make that denominator smaller, that'll make the overall ratio bigger. And that's the approach we want to take here. So in this case, so notice we can't do the same thing we did before. I can't like distribute this through in any way, shape, or form. I can just ignore the 0, I guess. But I can't like divide 340 over 340 and then 340 over 34. You can't do that. Not mathematically correct to kind of look at it that route. So in this case, we actually do have to go through the whole process here. So, and we're going to have 340 meters per second. 340 minus 34 is going to be 306 meters per second. And so here's the deal. You have decreased the size of the denominator by 10%. But when you decrease your denominator by 10%, it doesn't actually increase the overall ratio by exactly 10%. It's actually going to be by 11%. So as we'll see. But in this case, we will let our calculator do the heavy lifting for us. And so 340 divided by 306 is going to be 1.11. That's at 11% I told you about, but 1.1111. And then times 500 is going to be 555.5555. It's a repeating decimal here. And so in this case, I think we're shooting for 2 sig figs, so I'm going to have to actually round this up to 560, unfortunately. But it's 555.55555. It's up by 11%, not 10%. And so the idea again is that in the first example, we increase the numerator by 10%, it increases the whole number by 10%. But if you decrease the denominator by 10%, it actually increases the overall number by 11%. So just kind of the way it works. This is in principle how it works though, but notice, truth be told, I usually don't worry about the observer versus the source. If I see an observer or a source moving with roughly, say, 10% the speed of sound, I think it's going to change the frequency by roughly 10%. In one case, it'd be exact. In the case of the observer, in the case of the source, it would be close to 10%, but not exact. But in either case, that's my way of ballparking it just to see if an answer makes sense. Now, what if, on the other hand, this was not, we weren't worrying about sound, we were looking at the lights coming off the ambulance. So, and are they going to be red shifted or blue shifted the way a star would be and stuff like that, and by how much? And well, in this case, it's not going to make much of a difference because I'm not comparing my 34 meters per second to the speed of sound, which is 340 meters per second. I'd be comparing it to the speed of light, which is 3.0 times 10 to the 8th meters per second, 300 million meters per second. And as a percentage, 34 is again 10% of 340. It is not anywhere close to 10% of 300 million meters per second. In fact, it's such a tiny fraction of a percent that effectively it's not going to change the observed frequency of light in the same way. You have to have an observer or a source that is moving much, much, much faster if you want to see a shift in the observed frequency of light as compared to what we're seeing here with the frequency of sound. If you found this lesson helpful, consider giving it a like. Happy studying.